But anyway, thank you very much for the invitation. It's really a pleasure to be here. And I want to talk about the other Galois representation associated with an elliptic curve. So let me start with the setting. So let P of X be 3. And so we can define the elliptic curve E. And if K is an extension of Q, a characteristic zero field, we can look at the points of the elliptic curve. So this would be y k squared, such that y squared is P of X, plus we add an additional point, which is we should really be thinking projectively. So there's a point on the line of infinity where it meets the y-axis. We add this point and we look at the set. And of course, the amazing thing is that there's an abelian group structure. And there's a picture that goes along with that, which is that if you have your cubic curve and you intersect it with a line, it typically intersects in 3 points. And the group structure is defined in such a way that the sum of these 3 points is 0. And this additional point at infinity is the identity. Okay, so you get an abelian group. And the way that the group is defined, the coordinates of the sum of 2 points can be expressed as rational functions with coefficients in Q in terms of the coordinates of the 2 points you're adding. And that's clear from the geometry. So that tells you something interesting, which is the following: that if you know, let's say K over Q is the Galois extension, G, then G acts on. And okay, the classical theorem here is the Mordell-Weil theorem. Tells us that E of K is a finitely generated group, abelian group, when K is an unfit. On the other hand, if we look at the union of all number fields, if we look at bar, this is definitely not finitely generated. And we can actually say, as an abelian group, exactly what this is. So what is the situation with E of Q bar? Well, so this, of course, on the one hand, we can look at its torsion. So maybe I'll say the following. We have a short exact sequence from the torsion subgroup. This way. Short exact sequence like this. Now we can see what E of Q bar, what the torsion is. This is the same thing as E of C, torsion of E of C, because basically because multiplication by n gives a morphism from E to E, which is defined over Q. So all the points which are killed by that already lie in Q bar. And we know what E of C torsion is because, well, E of C has to be a compact Riemann surface, but it's also a group. So there's only one possibility. So it's got to be R mod C squared. So the torsion is going to be Q mod C squared. And we can look at group morphisms. Got Q bar over Q. And so as I indicated before, this group acts on this. In particular, it acts on this. So in fact, we have a homomorphism. And if you think about what the automorphism group of this is just GL2 over this ring Z hat for a finite completion of Z, the inverse limit of Z mod NZ over all n. which in turn can be factored as product over all primes L of GL to ZL. Okay, so we can look, as people usually do, one L at a time, and we get representations of GQ and GL2 of ZL. And of course, these representations are incredibly important, right? This is, one of the major themes of algebraic number theory over the last 50 years to try to understand them. And I mean, certainly this is an incredibly interesting thing to do. But I wanted to suggest looking at the other representation. That is to say, instead of looking at the action on the torsion part, look at the action on the V part. And I mean, E of Q bar is a divisible group. So if you divide out by the torsion, V is a uniquely divisible group. In fact, it's a Q vector space. So we can also think of V, if you like, you can think of it as E Q bar times Q. It's a Q vector space. Its dimension is infinite. It's easy to see that it's infinite dimensional. It's countable dimensional. And so V, the GQ acts continuously. And as usual, G of Q is not just a group, it's a topological group. Topology is defined in such a way that it acts in a continuous way on Q bar, where Q bar has a discrete topology. So if we think of V as having a discrete topology, GQ likewise acts in a continuous way on V. And it would be nice to understand this representation. In fact, it would be extremely nice to understand this representation. It would answer a lot of questions. So for example, one thing that it would tell us if we knew is so if we understand V as a representation, then, among other things, for every K in between Q and Q bar, we could look, so K just maps to, you can take invariance. And this will simply be Q. So the information of the dimension of the space of invariance for each K, like this encodes the ranks of the elliptic curve over all fields K between Q and Q bar, in particular for number fields. And in particular, if we just look at quadratic number fields, we can use the fact that I'll write it this way, that the rank of E of Q joining the square root of D is equal to the rank of E of Q plus the rank of another elliptic curve, the quadratic twist of E by D. So what that means is for D is the curve dy squared equals P of X. So if you know the ranks, the rank here, and you know the rank of EQ, then you also know the rank of the twist. So one question you could answer if you knew everything there is to know about this other representation is what are the ranks of twists of E? Are they bounded, for example? That would be an interesting thing to know. So in this statement, there's some H1 vanishing that's implicit there. Oh, I mean, like why? Yeah, I mean, yes, there is a, yeah. So I mean, of course, it's an infinite amount of information. It's hard to imagine how you could sort of state it. Let me mention another question, which I find interesting, although it's maybe kind of my own sort of twist of mind. But like, okay, we have the inverse Galois problem. We know, for example, that the monster group appears as a Galois group over Q. Does it ever happen that when you pass from Q to a Galois extension with Galois group, the monster group, that you get that the rank grows? If it does, then it gives you some representation of the monster group, like maybe the famous 196,000 some odd dimensional representation. Does that really happen? So I have no idea, but this representation would know.
What special probability curves in this passage? This is something you can do
for abelian varieties, for example, or yeah, absolutely. And probably, I mean, and not only over Q, you could do it over, for example, any finitely generated field. This would be a reasonable thing to do. And that's probably roughly the right generality to do it. But I mean, some of the things I'm going to say today require that we have an elliptic curve over Q. Okay, so yeah, so let me just say one very general thing, which is that we can write the representation as a direct sum over irreducibles. Look at irreducible rational continuous representations of GQ, W to the power of some multiplicity. So for each irreducible rational continuous representation of GQ, you have a multiplicity. And I mean, I should say, what do these things look like? By the continuity, they all sort of look the same way. I mean, you have a map from GQ to the Galois group of K over Q for some finite Galois extension. You have some finite group, which is a quotient of GQ. And then this is going to act irreducibly on some finite dimensional space. Right? So that's what all these representations look like. And so we'd like to know, for each such representation, what the multiplicity is. All right, so as I said, I mean, it seems sort of hopeless to describe this, but the point of this talk is the following question. I mean, GQ is an infinitely generated group. Even in the topological sense, it requires an infinite number of generators. And so any kind of statement of what the representation theory is would have to involve all those generators. It would be a kind of infinitary statement at the level of generators. And the question is there anything that can be said about which just involves a finite number of elements of the group? If there are, whatever the relations are that kind of constrain this representation, are they all essentially of an infinitary character, or are they some which can be stated just at the level of a finite collection of elements? And the conjecture which I want to state today is that they are all infinitary. That there's nothing. Okay, let me make a precise statement. Conjecture is if, I don't know, H contained in GQ is a finitely generated. So here, when I say finitely generated, this is a topological group, so I mean finitely topologically generated. This is a finitely generated subgroup. Then, if we think about V, if we think about V as an H representation, it's somehow as big as it could possibly be. That is to say, it's the sum over all irreducible Q representations of H of W to the power of a countably infinite number of copies of W. That's my conjecture. The largest it could be. And this should be true, for a billion varieties. It should be true, if you're working over finitely generated fields K. It should be true in characteristic P, except it's not true if you're a subfield of FP bar. You have to contain a global field to get traction. Okay, so
it's obviously true for a generic GQ.
Good question, and I'm going to answer that question. But before I do, let me specialize this conjecture because not because it's much harder, but it's again I'm trying to kind of look at the simplest situation in which you can formulate the questions. So rather than looking at all the representations, let me just look at the trivial representation. And so the conjecture is that the multiplicity is infinite. So E of Q bar. Let's say, right this way, E of Q bar H, the rank of this is infinite. And so to try to answer at least what I take to be your question, let me state a theorem, which is due to phi again. If sigma 1 through sigma d are independent, randomly chosen elements of GQ, and H is a group generated by sigma 1 through sigma d, so that which really means the closure of the group generated by these things, then the rank of the elliptic curve over Q bar H is indeed infinite. And the proof is actually
Wait, what does that mean? Probability.
with probability. I'm sorry. Yes, almost sure. Okay, so, and the proof is very easy. They did things in a slightly different way, but the idea is the following. We're just going to look at elements, points on E, which are defined over quadratic fields. And the way we're going to get these points is we're going to define Pn to be this thing. We're going to take x is going to be n. Maybe I'll use a different letter, Qn. We're going to let the x coordinate be n. The y coordinate is going to be the square root of P of n. Cheat. Yeah, it's absolutely a cheat. And yet this cheat is behind most of what I'm going to say today. Not everything, but most of it. Okay, so this is Qn. And of course, when you hit this with a sigma I, you're going to either get the same point or the negative of this point. Now, of course, it could happen that the square root of P of n is actually in Q. Okay, in that case, it's deterministic, but in that case, this is a. So you're not really interested in finding points which are defined over Q. You're interested in finding points which are in some other field, right? Some quadratic field that you haven't seen before. So you're really only interested. But fortunately, the Hilbert irreducibility theorem says most of the time this will not be a perfect square, and so you get something. And so there's a 1 in 2 chance that Qn will be there. And okay, you have d generators 1 and 2 to the d, and you repeat this over and over again. Borel-Cantelli, blah blah blah. Right. So it's pretty clear that generically this should be true. Okay, this is not very convincing evidence. Let me now kind of immediately tell you the most convincing evidence I know that this conjecture is true, at least in this setting. So let's do two Dutch rows. And it says the following. The Boltzmann-Dyer conjecture implies conjecture. But the conjecture here, I mean, if I've made 2 conjectures, I mean the second conjecture. I'm only going to talk about the second conjecture at this point. Okay, so in fact, you don't even need the full Boltzmann-Dyer conjecture. You just need the parity conjecture, which says that the rank of the elliptic curve is given by the sign of the functional equation of its L function. And let me try to sketch for you how the Doctor's proof goes.
Sorry, can I ask a question?
Please.
So you have another structure on these guys. You have this kind of height form, right? You have a quadratic form. Mm-hmm. Do you ever consider that, like among the infinitely many copies of W, does it get arbitrarily small? Is that what you expect?
Oh, like, that's a good question. I would think the answer would be yes, but yeah, it's a good question. But I don't know. Okay, so in fact, okay, so I said parity conjecture plus parity conjecture. What is the idea?
You really need to make curves with a large rank.
So
to use, I mean, the parity, you need to know there's points of infinite order or actually the high rank.
So, I mean, we're never going to use anything higher than rank 1. I understand your question.
There's a good chance that you could do much better unconditional.
Yes, yes. In fact, one of the reasons I wanted to give this talk was to address the analytic number theory. I never have a chance to address an audience of analytic number theory gathered here today to ask you. So, in fact, let me interrupt my comments about the Doctor's business and ask the following question. So, suppose I have elliptic curves. So elliptic curve over Q. And I want to know, does there exist D such that the quadratic twists, let's put it this way, that all the quadratic twists have non-vanishing first derivative of the L function.
First thing, put it at a half and we'll listen.
All right, you want to, your functional equations are S and 1 minus S. Okay. I want rank 1, and I would get rank 1 if I know that there's an odd -1 in the functional equation, and I know the non-vanishing of L prime. I know that there are quite a lot of Ds. If I have just one elliptic curve, there's quite a lot of Ds where this is true. I mean, if we go up to n, there's something like n to the 1 minus epsilon. So it seems imaginable by a probabilistic argument that I don't know how to run, that we could simultaneously. And if we could do that, then your idea would work. I asked Ivanits. Okay, so how did the Duchess argument work?
The reason that you're sticking to quadratic?
Why just use quadratic? Well, the answer is not really. I mean, quadratic seems to be the easiest thing to do, but at the end of the talk, I'll say something about another approach. Okay, so what do? What they do is they take an extension of Q, which looks like D1, D2. I shouldn't use D. D is the number of generators. Let's say M1, M2, MD plus 1. So this is a Galois group, Z mod 2Z to the power of D plus 1. And then they take, then you have these elements, sigma 1 through sigma D, right? These are the generators of H. And if you look at the invariance just of this field with respect to this group, because we have only D generators, then we're going to get a non-trivial. So let's call this thing K. K to the H over Q is at least 2. So this K, the H invariance contains some quadratic field inside this field. So as long as I did this in the wrong order. As long as the rank of E of Q adjoined square root of M is strictly greater than the rank E of Q for all square root of M in K. So in other words, all M, which are products of non-empty subsets of the MIs. As long as this is true, then I'm going to find, so this would imply that when I take E of Q bar H, this contains E of KH, which contains E of Q adjoined square root of M, which contains some point which is independent of any of the points that I get over Q. I'm not worrying about the repeatability of this kind of process, right? I mean, if I can do it once, I figure I can do it forever. And there's a sort of Hilbert irreducibility way of guaranteeing that's true. So that the difficulty is finding one guaranteed way of producing a point of infinite order that you haven't seen before. And so as long as you can do this, you win. Now, so what did the Dr. brothers do? They said, well, by root number calculations, we can find this. And if we knew this kind of statement, then you could okay, so this is from my point of view, this means that the statement is true, at least in the case, the second conjecture, and in the case of elliptic curves over Q. But it would be nice to have an unconditional proof, at least in some reasonably big class of cases. And so there are two situations in which I know how to give an unconditional proof. So, and also I'd like to say something about each. So, first thing is it's true for any collection for any h, put it that way, as long as well, as long as p of x factors over q. As long as the two torsion is rational over q, this is true for all h. It's the first thing. And the second thing is it's true for cyclic h. H has a single topological generator unconditionally. And the two arguments are very different. This is kind of a Ramsey theoretic argument, and this is an algebraic geometry argument. And I have no idea how the arguments are connected to each other, if they are, or how either of them are connected to the kind of arithmetic argument that I was sort of hinting might exist. So let me start with the case of the rational two torsion. Okay, to do this, I want to make a change of variables. So in case one, we can make a change of variables.
Sorry, which theorem are we? True is the first or the second?
Sorry, conjecture 2 is true. That is to say that the invariance, not necessarily all possible representations. By the way, the probability argument, is beautifully flexible. It will work for all representations. It'll work for abelian varieties in any dimension. I mean, but yeah, okay. I mean, that's obviously a very robust argument. This seems extremely specific. It doesn't, I can tell you, it works for elliptic curves over Q. You can make it with more effort work for elliptic curves over any finitely generated field. You can make it work for Jacobians of hyperelliptic curves, which are of the form y squared equals p of x, where all the roots of p are defined over Q. But it doesn't seem, I mean, I spent some time trying to figure out, yeah, I mean, it really seems limited to this kind of situation where you have a cyclic cover and all the ramification points are rational. So, well, Jacobians of such things, and maybe factors of Jacobians of such things, whatever. Okay, so in case one, we're going to make a change of variables. Namely, we're going to write the elliptic curve. It's a different y and a different x. We're going to write the elliptic curve as, let's say, x plus c. Variables I haven't used before. No, I have used c. rs dqrs. Okay, I mean, this looks like I'm kind of cheating if you don't know the story of elliptic curves. I mean, the issue is geometrically, you think of an elliptic curve as being a double cover of P1. And the branch points are the roots of the polynomial P of x, but there's also a branch point in infinity. So there are actually 4 branch points. If the 3 branch points plus infinity are all rational, then you can make a fractional linear change of variables on the base, and you can write the thing in this form. And I'm going to think of P, Q, R, and S as being positive integers. Okay, I'm going to write it in this way. And now I'm going to do the following thing. I'm going to let the generators through sigma d generated H. And I'm going to ask for each n. So for each n, I'm going to ask what happens when we take sigma I of square root of n divided by the square root of n. This is plus or minus 1. And so n is going to go to an n tuple. Sigma 1 square root of n over square root of n, and so on all the way up to sigma d square root of n over square root of n. So each integer is going to be assigned an n tuple of signs. Not an n tuple, a d tuple of signs. Okay, and I'm going to think of this as a coloring of the natural numbers. And now I'm going to invoke van der Waals theorem. which says if we color positive integers with finitely many colors, then we have an arbitrarily long arithmetic progression in one color. I feel like Discord. So van der Waerden implies that there exists a progression, which I'll call, I don't know, A plus D, A plus 2D, A plus some, I don't know. D is a bad letter. What should I call my common difference? K. I don't know why I have this urge to overuse D. Yeah. So let's say, I don't know, the length. Let's call it capital L K. So we have an arithmetic progression of this length where L is greater than the maximum of all of my P, Q, R, and S. And all these things have the same color. Monochromatic. And then what I'm going to do is I'm going to set X equal to A over K. And my claim is that if I do this, well, so what's going to happen? What's going to happen is I have A over K plus P, which is AP plus AP. What do I do? Not AP. A plus PK over K. And I have all the things, all the PQRS. This is equal to A plus RK over K. And the numerators all have the same colors. The denominators, so, okay. So if I multiply these things together, which is what I'm going to do when I plug X into the right-hand side, I multiply these things together, I'm going to have a K to the 4 in the denominator, that's a square. And the numerator is going to be a product of 4 things which have the same color. And so when I take the square root, it's going to be invariant under all CS. Okay, so this is a way. Again, this argument, I think on the face of it looks like it really is limited to Q. So that turns out not to be true. You can't use van der Waerden's theorem anymore, but if you use the Hales-Jewett theorem, which is kind of more, you can do the same thing. So. Another thing which is very strange about this argument from my point of view is, I mean, van der Waerden's theorem, if you are trying to figure out how big A and K have to be, if you have many colors, they're going to have to be very big. And the number of colors is somehow determined by the sizes of these integers, P, Q, R, and S, like the difference between the smallest and the biggest. So, I mean, the sort of thinness of the points you get in this way depends very sensitively on the elliptic curve in a way that's not very believable. I mean, clearly that's what's going on. Okay, so the last thing I want to say is if I want to prove, so sketch the argument of the following theorem. So if H is generated by a single element, then E Q bar invariance under H has infinite rank. And in fact, this couple of things that I should have said. Okay, I entirely omitted to say both in this van der Waerden argument and in the argument that I'm going to talk about now. Both of these are joint work. I'll just write it down now. These are both joint work with Bohe and Okay. And I mean, basically, Bohem was a student of mine maybe 20 years ago, and her PhD thesis was to prove this thing for elliptic curves over Q. And I mean, it's quite possible that I'm now overestimating the difficulty of the problem. I mean, certainly I underestimated it, suggested it. But over the years, we've tried different things, and a number of things have worked a little bit, but nothing yet has worked all the way. Okay, so but what I was going to say is that in fact the theorem that we proved does not depend on being over Q. It's true for a billion varieties, and in fact, maybe a better way of stating the theorem is the following. I'll say it's a slightly more general statement, but only slightly. So let be any field which satisfies the following properties. One, the characteristic of K is not equal to 2. It doesn't have to even be characteristic 0 as long as the characteristic is odd. The second is K is not locally finite. That is to say, it's not contained in FP bar for any FP bar. And the third thing is that the Galois group, so K bar over K, is cyclic, topologically cyclic.
How are these results related to Butzel's when you go in a Rawlik and Butzel in a cyclotomic tower and you look at the ranks? The Heigner points are eventually decided.
Yeah, so I mean,
they give you many points.
Yes, we did. We definitely did look at Heigner point arguments, and in the case of elliptic curves over Q,
Yeah,
which is not for these billion variety results, but for elliptic curves over Q and for H, which is generated has one generator, then you can use Heigner points to get the set theorem. That's work of Bohem. I didn't do it. Okay, so assuming all these things, then E, or more generally an abelian variety of K is even a rank. So this sort of fits into, if formulated this way, I think it fits in the people in field arithmetic have, which is that a lot of the Diophantine properties of the field should be controlled by its absolute Galois group. Okay, so let me. So I'm going to say something about the proof, and what I'm going to say is a little bit misleading. I'm going to sort of oversimplify it, but I think it tells you something about. Well, one way of thinking about the argument. So what we want to do is the following. We want to find a morphism from E P1, whose degree is even, and which has the following property. So if let's call this K as the field we're working over now instead of Q. Well, in fact, let's even forget about this formulation. Let's think about it over Q. So we have the function field here, and over here we have the function field of E. So this is an extension of degree 2n, and what I would like to say is that the discriminant is a square. So I mean, in fact, what we did was we looked at the Galois closure of F over Q of X, and we showed that the Galois group is actually an alternating group of size 2n. But what really matters is not that it's the alternating group, it's just that the discriminant is square. So we're interested in assuming we can find this. Of course, when I say it's a square, I mean it's a square of an element in Q of X. So if I specialize to a particular X value, then I'll get something which is a square. So in other words, if I choose some point, say C, from P1 of Q, and I look over E, I have points P1 through Pn, P2n, right? And if I think about the Galois action on these points, the Galois action will permute these points with an even permutation, only even permutations. Galois. Now, in particular, because the degree is even, that means that the permutation can't be cyclic. So because the permutation can't be cyclic, there must be at least 2 orbits. So choose an orbit. Let's call it, I don't know, P1, P2, PR. R is strictly less than 2n. And then add up these points, P1 plus P2 plus dot, 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 plus PR. Add these points up, and we get, okay, I just remembered why I didn't want to say this over Q. Yeah, I should be working over K. Right? I should be working over my group where the Galois group is cyclic. Because the point is that if the Galois group has a single generator, then yeah, then you can't have a single orbit, right? Because the orbit would be of even length, and that's what makes it an odd permutation. And so when you add these points which form a single orbit up, we're going to get a point in E, which is defined by K. Now, why don't I want the full orbit? Well, because if I added up all the points, I would always get the same thing, right? It wouldn't move as my point C moves. And all these divisors are linearly equivalent to each other. But if I just take a subset of these points, a proper subset, and add them up, then this will move in the family. And in fact, I'll get infinitely many independent points. Okay, so that's a fourth strategy. Now, there's another way of sort of thinking about this argument, which becomes relevant when you try to say, well, okay, why do I use the alternating group? So a second point of view on this geometry argument is the following. So I can look at E, so in this case, we were talking about E to the 2n, and divide by the alternating group A2n. And this thing will in fact be a double cover of E2n modulo S2n. And this variety over here, if you look at it, is something like E cross P2n minus 1. Right? It's not exactly a rational variety, but right, because I mean, what is an element of E to the 2n over S2n? Well, it's a divisor of degree 2n, so there's a divisor class, and then within the divisor class, so this variety over here has lots and lots of rational curves. But what we want is not a rational curve here. What we want is a rational curve here. Right? Because if we have a rational curve here, we take a point on this rational curve, of which there are lots. We take its inverse image, and now we have a 2n tuple of points on E. And so that's another way of thinking about how this game is played. So a kind of algebraic geometry question that you might ask if you wanted, so I mean, okay, so the alternating groups of even rank are sort of nice in the sense that like they have this permutation representation, this 2n minus 1 dimensional permutation representation where every element, even though the representation is irreducible, every element has an invariant. Right? Now, you could imagine a situation where you have a group and an irreducible representation, and any d-tuple of elements generate a group which has invariance. Right? That would be sort of a situation. In fact, that would be a situation which would be useful in trying to generalize the algebraic geometry approach from just one generator to d generators. And so the question is, can you do something like that? So what is the algebraic geometry question? So the algebraic geometry question is the following. So let G be a subgroup of Sn, so it's a permutation group, and take e to the n mod G. And the question is, are there rational curves? On such a variety. Well, the answer is complicated, and I think, well, we don't totally know. I mean, there are some interesting cases where there are lots of rational curves. So there's a very nice theorem of Larsen, who considered, he generalized from Sn to Weil groups. Weil group acts on the weight lattice or on the root lattice. I can't remember which one he used, and he tensored E with either the weight lattice or the root lattice, probably with the root lattice, and he divided by the action of the Weil group, and he showed that this is essentially a rational variety. So in some cases, you have an enormous number of rational points. Sorry, not rational points, rational curves. But I think that this is sort of atypical. Let's say about this. Let me conclude with an example.
Atypical meaning
I think
in terms of what G is.
I think it's an atypical example in terms of what G is. I think that having reflections in your group completely changes the character. And I think that probably what happens for almost any group which isn't a reflection group is that that rational curves are few and far between. That probably generically they don't exist. And I will mention, so I mean, this wouldn't be kind of useful for the arithmetic application, but just sort of a geometric question I don't know the answer to, but I wonder about it. Suppose I take e to the n and I simply mod out by z mod 2c, acting by plus or minus 1. Does this have any rational curves? Forget about over q, just over c. There's a theorem of Galois which says if A is general abelian variety, maybe very, very general, some very general abelian variety of dimension greater than or equal to 3, then A mod plus or minus 1 has no rational curves. But part of the proof of this theorem involves saying, well, if you have a very general abelian variety, it's simple. So it doesn't really tell you anything about what happens. Theorem with him and Simon John, we prove the following. If n is greater than or equal to, I think, 13, and E1, E2, en are sufficiently general, then E1 plus plus en mod plus or minus 1 has no rational curves, no, let's call them diagonal rational curves. There's sort of stupid rational curves. You set all the coordinates but 1 equal to 0 and so on. I mean, there's rational curves that sort of don't span, but this is generically, it's not going to have any diagonal rational curves.
Sufficiently means you delete a countable set of
close conditions, right? And so, okay, so we have this statement, but we don't know that if it's the same elliptic curve, like e to the n mod plus or minus 1, we don't know. And of course, plus or minus 1 is just sort of a test case, just trying to come up with a group which doesn't have, which is sort of far away from being a reflection group. We really don't know what to expect, but that is another possible approach that could happen.
If you just assume that your EIs were pairwise non-isogynous or something, that wouldn't be enough.
Yeah, so, I mean, no, it isn't. Though it might, well, let's put it this way. If n is equal to 2, then for any two elliptic curves, you're sort of in a K3 situation. K3s have a lot of rational curves. So it might be true if n is big enough, but at some point we thought we could prove that we ended up proving something weaker. We don't really know what happens for it. So that's it.
What kind of H's can you deal with besides cyclic?
So, I mean, there's specific cases where we can. So, I mean, just to give you an example, sort of a stupid example, but for example, there's a way of using the Hamming code to show that if you take the elliptic curve, which has complex multiplication by the square root of -7, and you have a group which is generated by 2 generators, the theorem is okay. So, I mean, there's kind of, I cited results like that, but really the answer is no.
Any questions? I'd like to thank the speaker again for a very tough.